So thank you everyone for coming at our Tech Talk. That's our first session after a long break. I am delighted to introduce Jobayer Hossain, one of our own ACCEL-CTR biostatisticians from Nemours. He's a long-time and very active member of the ACCEL-CTR Biostatistics Epidemiology Research Design Core, or BERG, and obviously our speaker. But before I introduce him, let me mention some housekeeping issues. All the CME credits are on the screen, and we can also email you instructions if you provide your address on the sign-in sheet. We have a sign-in sheet? Oh, okay. Tomorrow, we have an ID series, and it will be Dr. Jason Jones from Health Catalyst. We'll talk about quantitative support from health equity prioritization. So that's going to be very interesting. Also, don't forget to register. And the full ID series schedule is posted on the ACCEL-DE-CTR.org. And finally, our next Tech Talk will be October 3rd, and that will be also one of our colleagues from Nemours, Dr. Erin Krauji, who will talk about the promise of precision medicine, a focus on genomics and translational bioinformatics. So I'm really delighted to introduce Dr. Hossain here. Dr. Hossain has multiple titles. He's a senior research scientist in biomedical research at the Nemours Children's Health System. He's also the manager of the biostatistics core at Nemours, and also adjunct associate professor in the Department of Applied Economics and Statistics at University of Delaware. He obtained a PhD in statistics from Southern Methodist University in Dallas, in Texas, and interesting fact, began his career in statistics by being the assistant director of the central bank in Bangladesh. He has more than 100 publications. He was a PI of a COBRE pilot grant and has been co-investigators in multiple federal grants. And as I mentioned before, he's a very active member of our CTR Biostatistic Epidemiology and Research Design Core. So thank you very much, Jobayer, for coming here, and we look forward to our.
Thank you, Claudia. And thank you very much to all of you for being here, and also all of you online. Yeah, today we are talking about the classification of longitudinal data. And you know that longitudinal data, we have different kinds. Like one is you can collect the longitudinal data like at the same common points of time for everybody and maybe equally interval. And another kind is kind of unbalanced, means necessarily, for example, necessarily collecting data. It would be everywhere, and you may end up with a unique sequence of the collection of time over time. But it is very important today, classification of longitudinal trajectories. And longitudinal data, you understand that it gives a overall video type of picture of something if you want to see, whereas cross-sectional data is kind of like a picture, taking a picture, and the longitudinal data you can view as a video. So today we are talking about the precision medicine. We are talking about the learning healthcare system or precision personalized medicine. Whatever we say, the main goal is to identify the things someone needs or to model individually, and then for the precision medicine, you see, or learning healthcare system, you see, you try to identify a classes of within classes are homogeneous and like the between classes more heterogeneous or distinct. So yeah, here is the presentation outline. Of course, will be background and motivation. Then we'll talk about the heterogeneous linear mixed model as well as growth mixed model, whatever it is, they are the same kind. And then I will talk about we can do in another way, like host of kind of analysis, and then we'll compare the classification of different methods. So background, as I said, classification of longitudinal heterogeneous trajectories in distinct subgroup is a topic of growing interest. Of course, we know, and that's what we talked about. Necessarily occurring data, such as electronic health records, have shown great utility currently in learning healthcare systems and personalized medical decisions. But when we talk about the naturally occurring data, observation time or the measurement times are often irregularly or unequally spaced and vary across individuals. As I said a minute before, you may come up with maybe unique sequence of measurement for each individual. One of the problems, like when we usually plan the measurement at a common set of time points for everybody. One of the things you do, you measure and you do the analysis, the mean profile you can do. But this type of data, you do not have that scope. One way you can do, you can express the data as a function of time. I mean, functional statistics. And of course, then linear, we have no other way I know for analyzing that, like unless you think, okay, I have 5 persons, I can individually do, but we are not dealing with 5 persons. Currently, in the data science time, we are handling millions and millions, thousands and thousands of people, right? Or individuals and large data set. So in this situation, mixed effects regression are being used, and it does very good and performance in analyzing. It does in like as a combination, it models the data as a combination of average trend for the whole population that is actually shared by all individuals, and as well as it also models individual variation from the average population. And that is the beauty of the script model. Means you have the access to the individual level, as well as you are talking about the main goal to model the group of the people. So again, no matter what we say when we deal with the analysis of unbalanced longitudinal data, I can't think of any other thing except the mixed effects model or like that. That is the standard. The general form of this is here. I don't have any pointer, but see xi beta. Beta is the population parameter that describes what? Population characteristics, or that describes the population trend. And the small bi, lower bi, that is the vector of random coefficients related to ith subject. And it indicates how the trend over time for the ith individual deviated from the population trend. Our goal is the population trend, but we need to know the heterogeneity of the population, like individual level of the heterogeneity. And this is the most important. So beauty of the mixed effects model is the actually random coefficients, not the fixed effects. Fixed effects gives you overall idea about that, characterizes the, or it tells the shape of the trajectories of the overall population. But the main thing is the random coefficients. The assumption of the random coefficient is like it is multiplied normal even if it is not normal, but it needs to be something close to be that. But it has the mean 0 and the variance covariance matrix D that is actually like shows some kinds of homogeneity. We know the shape of the normal data, right? So the assumption is that trajectories, individual level trajectories, they cannot be like too much heterogeneous. One is going very up, one is going very down. Then, or many other way, what happens is too many heterogeneities of this deviation. It's simply that means it shows a several subgroups in the data or in the population. One of the problem of these subgroups, and if we use this model, and that is the standard model we have in the literature, in the softwares. And one of the problems, we may miss the important features of the even population trajectory, as well as it will mess up with the individual level things, right? However, beta is being a fixed effect. Our goal is to see, like, as we know, if we have a group of people here, and suppose we are trying to characterize something, and maybe if we characterize everybody together, it may not be very good because we may lose some of the information from, or when we estimate something, we want to bring the things that can represent to every individual in the data set. But when it is not, what we do, we need to first identify is there any subgroups that can improve our analysis, or that may have different shapes, right? So that is important. And then you do the subgroup, like the estimation for the subgroups. And that is the right way of analyzing. But if instead of doing that, if we use we call this as a like the mixed effect model under the homogeneity assumption. So now think about this. As long as it is a good, like the model, basically like the beta here, that is the fixed effects, and without loss of generality, if we think actually that is a constant. What is BI actually doing? It grabs all the heterogeneities existing across all the trajectories of all individuals under the analysis, right? And that's what we need to do and grab. There's the data for the further see, like if there is any like the subgroups or Barbeck et al. Actually investigated this, and he suggested a mixed model of the BI theoretically. That is good, and that is the idea we need to do. And he suggested like doing mixed model with the mixed effects model. And here is the obviously, like now here the top D, like we have, this is like within group, within subgroup or within component. We can say component also subgroup as it, right? We can within group correlation matrix of the random coefficients. That actually classify everything. You can do it. If you think about the cluster analysis, if you think about the other multivariable analysis, what we do, we look at the similarity or dissimilarity or the distance function or the correlation function or the correlation matrix, right? All these things gives us the idea, the similarity and dissimilarity. Anything we can do here, considering BI as a data as a for the post hoc analysis, like you do a perfect analysis in the model as much as possible, and then grab the BI, do the post hoc analysis for the do any kind of cluster analysis, and then you will have actually see you will see like the if there is any group and how they are different from each other. But here Barbeck actually did, and see here when we suppose the D is the within class, suppose we have G component, we do not know. So when we have some defined group, like for example, we have here many of them, we know some of us, if we consider the gender as a characteristics, some of the male, some of the female, it's a defined group or classes, right? But when we do not know the grouping, or we do not know the grouping, then what we do? We say that is the latent class, and like mixer model or conventional cluster analysis does that using the data and take the patterns of the correlation and those things, and then they classify the data in groups based on their homogeneity. So here they have the D-CTR is the covariance matrix for the whole data, and then D is the within group components covariance matrix, and then other thing is extra than our usual assumption. One thing when we deal with this data, like although we consider the BI as a data for the post-hoc analysis, but it is not. We need to estimate it from the data. That means condition, and that is the condition we have. Here is the CPI estimate or prediction. Basically, when we have some random variable, we do not say estimation of something. We usually say prediction, but still I will say here estimation. But I mean predicting, but you can say a term as prediction. But and this is the predict like the best linear unbiased predictor. Like those who are taking to the probability, you know that expectation of conditional distribution of two variables will provide you the best unbiased, best linear unbiased predictors. And that's what we need. We need to have a good estimation because we are not using the data directly, and that will reflect or that will describe the trajectories for each of them, each individual, and that's what our goal. Try to model as good as possible. And here you see here now here you see like the mean of this model is xi beta, right? Fixed effects, right? Because like random effect is 0, but here it got changed because we have now component mean actually for the component with the assumption of the component trajectories, right? And this is the mean. If you want to go back of the homogeneity model, you need the assumption of this needs to be 0. And this is the estimation at this current level with the model of Barbeck's model for the heterogeneity using the mixer model. And then you have, this is the usual one we saw just a minute before, we saw here, and this is the whole thing the same for the component, this component. But other part, that is the correction for the heterogeneity. And where this correction part actually take the things towards the mean of the component and proportional to this is the posterior probability of being to be in a class. It is a lot of parameters you need to estimate. The computation, still I don't think it is very easy or straightforward because of the complexity. I know people are going to Mars or Moon, so why it to be hard? To not be. I hope someone will do better, and then we'll not have trouble. But we have a lot of troubles now. Although it is a very good model, but computationally it is not too easy. Often fails. Yeah, this is the pi we used in the term here, and that is the posterior probability of the ith individual to belong to the tiered component. Suppose you have some component, some subset. Component means subset. And we term at this situation, we term this model as a heterogeneous mixed effects model. We don't have that in the usual. It did a long time before. After that, and he implemented in a SAS macro, but it was able to handle maybe very small data set. And also, computationally, EM algorithm was found very computationally expensive. And of course, also had the problem of value estimates of the variance parameters. Without variance parameters, any estimation is like the almost does not say whole story. Recently, Proust lemma defined an extension of this model. See there, we say D as a common, right? But he did not vary it from component to component. And here, like Proust lemma, they actually vary, and they use a weight point with the common one in front of that. The weight things to, and that is says class-specific intensity of individual variability to make some changes or some class-specific variation to include and add. And they used Marquardt algorithm that they think minimizes the EM algorithm, and they implemented that in LCMM. Very popular now, but most of the time, how it fails, we will see that also in a few minutes. But this one, although the Barbeck is the introducer of the idea, the popularity gain, actually Mutain et al. Introduced a similar method that combines multi-level as well as mixer models of the same idea, but he implemented M+ in M+. M+ is a, like you will see in the psychometry or socio behavior data analyst, M+ is pretty popular. There's a growth mixer model. And actually, Mutain et al. Introduced a similar method in M+, and it gained actually popularity and named as a growth mixer model. Both the method, like what we talked about until now, these are the two things we have. We do not have mainstream, like nothing to do to handle this, like in SAS or other mainstream statistical software. Both methods has limitations, and we will talk about some limitations of these two methods. Yeah, computationally complex fairly quickly because it has a lot of parameters, and like the computational complexity increases and get difficult, like that become more problematic very quickly. It increases the sample size as you increase the sample size. Also, number of measurements for like individuals, as well as degree of unbalancedness, how it is, and how complex you are fitting a curve. Is it a straight line? A straight line means you don't have anything. For a straight line, what we need to describe everything? Intercept and slope, right? But depends on how complex is your model. And of course, how many number of random effects you need to use. It like exponentially increases the time of computation time. Another problem that is actually inherent problem of the most of the cluster analysis as well as for the mixer modeling. You suppose we do not know, we have it, we do not know how many groups would be there, right? So in mixed model, including that, because they use the mixed model idea of the mixed model, right? So we need to pre-specify number of classes or number of groups. Number of selection actually, like the fit statistic or the post-fit criterion, and like BAC or AIC, they shows you to select some numbers which would be optimum or which classification would be optimum. But believe me, it's not that easy or straightforward. The things is that you have to be perfect, and the person who handles, the person also need to know everything. Most of the thing, like see, most of the people you go, oh, I used R function for the Institute's model. But does it make sense always? No, because for the analysis, first we need to see like the visual inspection of the curve, how it is. Then we need to set a model, right? And then we need to look at other criteria, model fit criteria, only then it will be. And another problem of these log-like functions have many maxima points. Like one of the thing, what we do, like if you have unimodal, we want to measure get the maximum, like one maximum. But if you have multiple maxima point, then you are in trouble, and that's the trouble we have here in the like-to-like function. And that's why sometimes you need to choose a good initial values to avoid the problem. Another problem, or even the current version what LCMF has, that like you may reach at the highest iteration, but your program may not converse. If it does not converse, you will not have a valid estimation at all. And on the other hand, GMM has good work performance in the M+. That one has good performance in terms of the handling is small. It cannot handle like large data set or with the many like the too much like unbalancedness in the data. I mean, that's what I say here, assuming limited number of observation per subject with common measurements at the time. If it is not, you can do like you can thin the data and you can align to nearest time points at certain time points, like round point.
Your question,
yeah.
if I may. When you talk about degree of unbalancedness, is it the difference in the trajectories that
No.
unbalanced?
I mean, for example, think about the data we have, the EMR. So if you have unbalanced, means here, we collect the data on their visit. And see, these visits are completely different from each other. And number of visits also. So when we say unbalanced, we mean it is balance is longitudinal data is balanced when suppose we have a plan data, and we can plan well everybody will measure now and maybe 10 minutes later and 15 minutes later at a certain and common time point. Okay. That is balanced. And here it is unbalanced. Because you collect the data everywhere. One of the good things of the collecting national data is you have the continuity of the trajectories. You have the data, maybe not from one person, but at least everywhere from, if you consider everybody of the same type, that will give you the continuity. But in one of the limitations of getting from the same common time points is we may miss some information. We do not know when we collect 6 now and 6 months what will happen within these 6 months. But when you have the continuity, it is hard to analyze and you have to know how to do that, but it gives you the continuity of the function or process. Now, as I said, my goal, of course, we have some limitations using these two things, and that's available we have now. And no other mainstream like the software has anything. And in that case, what we can do, like if we have trouble, okay, we can do that. As long as we model nicely, and then we know that BI contains all the heterogeneities. Why not we do that? We take it and then we do the cluster analysis, the one best fit the data, or the one best fit the data. Remember, in the cluster analysis or classification, there are two problems. One is classification, like the accuracy, and another one is to identify the optimal classification. We do not have, even for the simple data also, we don't have many things to identify for the class, which classification is the good one. So, of course, the method I say flexible because we are going for the, we are not going for the complex computational things through the, as long as it is like any mainstream statistics software you have, as long as you have the facilities of the mixed groups model or cluster analysis, then at least you can find something good from the classification. And of course, the complexities are not severe because we do not have that many parameters we included in the model. In this presentation, we have 5 data sets. We will see how these methods are doing. And of course, data set contains 2 to 3 subsets of growth, early childhood growth patterns from 0 to 5 years by group patterns. What is growth pattern? How will define growth? Patterns of linear, quadrant, and cubic trends, but how will define the growth? We are talking about the weight per length for ages less than 2 years, and the BMI for the greater than or equal to 2 years, and these are the two common measures of somatic growth under the age of different age groups, right? So we are following every individual from the 0 to 5 years. We collected the data retrospectively from the electronic health records. And of course, like the data originally collected at the clinic visit during the first 5 years of their life, 0 to 5 years. And after calculating the port length and BMIGs, we used standardized scores of these two indicators as a growth indicator or growth index. And we can do that because the standardized score, same quantile point you see, same quantile point actually used for the weight status when we say under like underweight or lean or overweight or obese, we define for these two indicators in the same quantile points. That's how we can connect it to measures. As I said, like the way we are trying to use the best linear unbiased predictors. Again, this is the same thing, and this is the prediction error for this one. And some of the steps here, like as I say, grab the idea when you have the data. Look at how your mean response trajectory or shape. Try to get the shape and level of the mean response trajectory, and then have a good model that represents mean response trajectory and along with your individual or random coefficients with the nice random coefficients with less error. Of course, it may be linear, it may be piecewise linear, or it can be other polynomial functions. And when for the node, we have to select the nodes based on the peak, AIC or BIC peak. And of course, we need to do a grid search for that. Then once we model nicely, extract the empirical best linear unbiased predictors, perform suitable cluster analysis, and then second thing is we can do many analysis, right? Then which one is best? How will we know? You have to do. For that, add a classification identifier and its interaction with time in basic model at step 2. How you have many identifier now, classification identifier. Use all of them one time to see which group fits the data best, right? And of course, the compare the goodness of fit statistics and use that as the one give you the best fit statistic. Select that as the optimum model. We use actually for these data sets, we use many of them like the TAS, R, and SPSS, IBM actually two-step methods also. But I mean, among many methods, you know that all the clustering, even conventional clustering, they do not perform similar level of accuracy with the same data. One does better than others. There are some criteria, but still sometimes it's better for you. These are more that's why this is called exploratory. You have to explore more than it is what it is written. Which one does best? We can skip this because we are talking about all kinds of cluster analysis you can do, but one method is the mixer model. Again, we have 5 data sets of 2-3 components with varying extent of separability to evaluate the classification. Again, one of the things of the classification is how distinct the groups, how the distincts of the components. If they are not very distinctable, then classification will give you trouble. and also how sensitive your algorithm to crash. Even the overlapping would be there in natural data. You never think that it will be completely distinct. So how that is how sensitive the algorithm to grasp still the or to classify. So we have generated a classifications of 2 to 5 groups, and we have used the M plus, which will say GMM for this one presentation. We also used RLCMM for case. We will say HLME, and also I say, well, I will not go that complicated now, at least for now, because of the complicated. Yeah, I will do the BLUP and do the post hoc analysis, and then directed BLUP. And you have the data. You do not need to use the data yourself. Sometimes if you use like some Latin variable methods or like principal component factor analysis or canonical correlation, you reduce the data dimension. Basically, sometimes it seems that like out of 12 to 13, you can only 3 or 4 data set can bring all the information, and it actually aligns the patterns and sometimes makes easier. So yeah, BLUP as well as clustering, principal component analysis of the BLUPs, all those things also, right? And then we used like that for this presentation. I have the R package and class for this. All of them also. And then for the evaluation, and GMM in M+, they have their own evaluation, how they did. And also HLMA, they have the fit criterion, and as well as the method for the evaluation. I say that also I have for those classification as well as our classification. Here is the data set. And I will say, if you look at the trajectories, it looks like they are pretty distinct. Like this is a kind of a linear trend. This is a like kind of come down and a little up, right? And if we consider 3 of them and pretty 3 components, and we see how it does very fast method that is in the done by the M plus GMM as we name there, and see when we know there are 3 groups, and see here they did pretty good to identify all the patient, all the subjects in the same group, right? The HLME also did very good in the identification. The BLUP or BLUP LNT, they also did very good identification. In terms of the evaluation, how they did, every method suggested this one and number 3 of their classification as the best. Yeah, it seems that this is pretty separable data and pretty distinct components are there, and so all the methods did perfectly. And of course, we did not deal with so many data sets, like so many numbers of the patient. It is just only 254, 83, and 50. So one of the situation, we do not know how many classes, number of classes will be the good one for the classification. I tried with the 2, and here GMM actually did first one and third one in the same group. Here that one actually divided everything. This one also did first one and third one in the same group. And then it may be because like here is a little little something increasing. Here is after some time it is increasing, but here is going up and then down. But in any case, they are different. But here, when we squeeze to two groups, because we do not know in the real situation how many groups will be there, but still we have to rely on these numbers, right? But good thing is that all those numbers actually matches and agree for this classification.
So I have another question. So are all the children here classified? Because it seemed to me that you had a much larger data set. Or are you only showing 3?
Oh no, I mean like that. In this data set, we have 3 distinct components. One component has 54, one has 83, one has 50. The total number of patients we have here only this many. It's not 3365. From 3365 patients, I tried to find out different components and then merge to bring some of the classes to see some of the data artificially to see how our classification programs are doing to classify them. This one also have like same kind, a little here is a little up but with more variability. And again, still all 3 groups did good job in classification, and the same thing, they did the good job in identifying them. Here, this component has a lot of variability basically, and little less distinction if you see in the population trend, less distinction, and you see DMN actually group first 2 in the same always, even for the 3 grouping. And this one also did, and then third one they grouped as 2 different EA, but this one at least try to grasp like the more and also like did here like got more, except this lost 43 with 102 merging, and here did only 11. I mean, in this data set, in these 3 components, like they are not too much distinctness. Like it has to be how sensitive your data to find if there is some distinctness somewhere, how you can collect it. And that's how they try to get it. And these 2 actually put all of them together. And when we did the 3, and then it is in the same group. And but however, here it is a little better than them. How it was 2 groups, like completely 2 different kinds of components, right? One is up and one is down, and see, as we have 2 components in the data set, we try to see how they do. Like M+ did very good job getting everything, and here they actually did half and half, and we see their classification half and half. Actually, not a good classification at all. And then this also did very good. This also did very good. I mean, and then of course for the M+ classification, you see like the evaluation. They say 4 is the best classification. Here is the 3 is the best classification, and the 4 is the best classification. But no, if you do the here, our classification, evaluation, at least this shows that this is the best classification. This one also shows 2 is the best classification. 2 group classification is the best. Here again, we have the two, and then DMM did very good. Here, HLME did very good. Yeah, not did very good because they merged actually still, both of them. See, when we did three, then HLME they put this one as a one group and they divided this as a two groups. But it is still better at least they put one component at one place and then divide other group. And that's why they selected, actually even they selected this one as the best, three as the best. However, we found here like the two is the best. We need to finish up in 7 minutes, so let's go to the discussion. The things that when the classification problem, one of the things that we never know how many distinct groups or components may have in one data set. So you keep classifying and then identify which is the classification. So one is the thing that accurately classification, and then second thing is the evaluation. Two things. For the evaluation, like one situation is we know here data set have three components, two components, we know. How did we found here? And then we saw that when the same grouping for the three in the data set component and three, which algorithm did identify the three as a three. We found that like first time BLUP and T means like the found was able to identify all of them, right? And DMM identified 4 out of 5 data sets. HLME identified 2 data sets, like first 2 with the distinct 3 grouping. Then it failed actually for the 2 grouping, surprisingly, because even for the 2 group components we have, it shows like it was showing better performance as we classify more with the as we classify with the more number of classes. And of course, for the evaluation also we saw that mixed effects model that's good, because we know that in the mixed effect model, suppose you want to see how the in a dataset, longitudinal dataset, you have a group variable. We want to see the best fit of the data, right? For each of the group, right? So we are using the same concept. So it does actually pretty good job. And then like these things actually I said already, clearly separable. When clearly separable data for the 3 components, we see all methods did the same job, same performance. 2, when it was 2 component, we did not find HLME very nice. However, GMM did good, but the problem of GMM data, you have to have very small data set, and you may not have too much unbalancedness of the data. And methods differ substantially when the data sets have less separable components. And when we squeeze, actually, same thing we saw, GMM, BLUP, and BLUP differ from the same, more or less same trend in this small data set. They are pretty small, they are not very big. And sometimes HLME did, sometimes not. The conclusion is, no matter what the methods you used, at the very beginning we say, for the unbalanced data, you have to have the function of time, right? And then only mixed effects model allows you to fit the functions, right? It gives the population level as well as it gives the individual level. So no matter what you use, you have to have you have to fit the model accurately. And then as long as it is separable, it fits very well, although we didn't find much good better in the HLME with the 2 groupings. And BLUP and BLUPs, using the BLUPs is the easier. You can implement in anywhere, and it does not have much computational burden. I tried with my 655 data. Of course, we could not do anything in the, you cannot go with those things with that. And plus, but did long time 39 hours to run or something like that, but most of the time it failed to give you, they put most of the things in one side and maybe one or two and other side. It means it runs some way with very forcefully and tries to estimate so many parameters, and the estimation may not be adequate to have some distinct points. Of course, it is very good as we are talking about the precision and personalized medicine. Of course, we need to have the methods that can handle. As long as we do not have the computational things improved, at least we can go for the post-hoc method. And that is the conclusion of this presentation. If you have any question, thank you for you guys' patience. And of course, if you have any question, please let me know.
I have a question.
Okay.
Okay, it's more in clinical application. So you have all these trajectories and these methods that identify, one or the other better. But so once you have defined your trajectories, can you define specific characteristics or characteristics of the patient that are specific to each of these of these trajectories and differ? Because then how do you select what is the best, whether you need 2 or 3 or 4 trajectories?
Yeah, that's what.
And I guess, how do you use the characteristics of the patients, for each trajectory to select which method and which trajectory of which number of trajectories is the best?
Yeah, that's what we have the evaluation here. Like I said, like we have a base method at the beginning of our step we used, and then we did the classification of many of them, like 2, 3, 4, 5, and then we put them in the base model with the timing. As the function is time, then timing, each indicator separately in the one model, and then put the interaction with the time, because this is the function of the time, and then the model will to see which classification of we have the whole data set, which classification actually treat the data considering each of the groups as a different, and which one gives the best fit of the data. Yeah, best fit. And then the one we have the fit statistics suggest like that, the one we will like that take as a best fit model.
And then you look at the patient's characteristics to see whether they differ.
That's what actually you do the classification cluster analysis, like in the cluster analysis. First you do the clustering, and then you classify or characterize the within group individuals, how they are characters and how they differ from the other groups.
And does it happen that you have a few patients that doesn't enter in any of these trajectories, and what do you do then? If you have 3 or 4 trajectories and then a bunch of patients who are not.
Maybe a few of them would be, and they might be outlier with their trajectories, and we have to see still which group they can be fall. Of course, when we do the classification, they will go in some, like we have the individual level trajectory characteristics, and that actually have the shape of that individual. And classification, like the cluster analysis, the way it does the heterogeneity based on that data, right? So when you have the shape of the individual level shapes, you are using everybody's individual shape, and even some outlier, they may form a small group. It is up to you whether you will keep them in the group or you will bring to them in another group that will have a slightly similarities with them. So even though model, but everything of the classification of is kind of exploratory, you have to use a lot of judgment still. And very first thing, you have to see how your population is behaving. And then grasp that, and then you are modeling both together, a trend for the population, as well as you have the trend for each individual. But remember, your population trend has to be the perfect one, or the most accurate one, most representative one.
Any other question? Well, thank you again.